everyone to the industry track with Zaina Nabusi from the University of Warwick. She is a PhD candidate in structural engineering. She will be presenting to us metal 3D printing in structural engineering. Just few words before Zaina start, I would like to say about her. Zaina is a civil engineer who specializes in structural steelwork design. Can you mute yourself, please, Zaina? Okay, thank you. So as mentioned, Zaina is a civil engineer who specializes in structural steelwork design, metal 3D printing, and modern construction technologies. She has 3 years experience working as a structural engineer in the DAR group, where she was involved in designing international and large-scale steelwork projects. Designing such challenging, innovative, and costly superstructure made her realize that she must pursue structural engineering at more advanced academic level. Currently, Zaina is busy with her PhD at the Warwick University, as I mentioned. Her research is on the potential of metal 3D printing. She strongly believes that this is an exciting method of manufacture, can be used for full-size steel components in the future. In 2019, Zaina received a Commandment Research Award in the structural engineering organized by Midland Counties Regional Group in the UK for a research paper called The Potential for Metal 3D Printing in Structural Engineering. In addition to her full academic and professional involvement, Zaina is a STEM ambassador and for 5 years has been an active member of Midland County's Young Member Group of the Institution of Structural Engineer. Welcome, Zaina, and thank you for making time today to share your metal 3D printing in structural engineering view. You may share your screen.
Hello, everyone, and thanks for the nice introduction. I'm excited to be here today. I think it's a big day for all of us, and it's nice to see how we're encouraging women, how we start encouraging each other. Yes, this is... thanks again for the introduction. I'm just... Sorry, yeah. This is me, as Malika introduced. I'm a civil engineer and currently a PhD candidate at Warwick. My Viva is next week, so it's a big week for me. And currently I'm a part-time structural engineer at DICE in Manchester. This is me while doing the printing in different collaborators. And in 2019, we got a commendation award from the Institution of Structural Engineer on a research paper that submitted, and we're trying to push the construction, the aim in construction further. Also, I've been lucky to introduce my research outcomes in different conferences in Norway, Australia, China, and the States, and different places. So I'm really excited again to be here to share awareness and maybe to inspire a younger generation to take this technology forward and push it more. So the more we talk about it, the more we believe in it, I believe. So what's happening in the construction industry? This is what we're going to start. What was the motivation and why we need to talk about it? So we've seen a lot of updates all over in all profession and how they start using the 3D printing. We've seen it in the medicine, we've seen it in the automotive, we've seen it in gas and oil. You can see how it's start helping us all. So the question was for us as structural engineer or construction, why not us? Why not us? When I started in 2018, I started seeing the growth of concrete printing and construction. We've seen how from its early stages till 2008, it was in a steady stage, but later on from 2008 till now, it's an exponential growth. There are also a key marks projects that's already been in the industry, and we heard about companies that start printing houses in 24 hours. We've seen people living now in 3D printed houses. We start seeing it's going global in all countries, each country. And it's all started here with these are key milestones project that we will always see them when we're talking about concrete construction. the Apple houses in China, and how Dubai is trying to push the AM industry in construction to have a minimum of 20%. So all buildings have to have 20 or to 30% to be 3D printed in 2030. So we've seen how it's being pushed. Taking that forward from a 38 meter square concrete house to 640 meter square house in Dubai, and you can see that here. The yellow one was being printed in a cold weather, however, the opposite, it's been in hot weather. We've seen in Italy houses that have been printed from soil. So we can see how all these development coming forward, not just in houses, we've seen it also in the bridges. So these are two design bridge. The one in 2040, Paris is working toward printing a 40-meter span pedestrian bridge for the Olympics. And we already seen the bridges in Amsterdam with 30 span is on site. This is all about concrete, but how about metal printing? And where are we in the metal 3D printing? So also, just looking at different scale, we've seen different scales here. We've seen in 3D print and metal printing in 2018 when it started that we have that replication of small columns done by Imperial, Arab's connections about optimization, the micro lattice structures. We've seen a seismic damper. So we've seen small key elements that started. And of course, all of us heard about the MX3D bridge that had pushed the horizon in the AM printing and show us what we can do in a larger scale aspects. So these are the development in the AM, the early stages development. There is much more, but these are the key starting points. And we've all seen in 2021 that finally the MX3D bridge is on site. After a lot of tests, if we heard the journey apart from printing, designing, the approval and the metal testing and all this, because of our classic step construction, because it's our safety, we need to make sure everything is safe. So I'm talking about here about confidence in materials and our safety. That's might tell us why it's still slow in the construction. I've shared different applications and we can categorize them in 3 main points. We can see how we are redesigning structures. The redesigning could be for structural and for non-structural elements. For structural elements, we've seen the beam columns. For non-structural elements, could be in the cladding, could be in windows frames, could be in fake connections, just as studying things. So we've already start seeing it. And the enhancement, the enhancement could come from different applications that I will talk about, and we already seen it now with the dampers. And the question is how we can take it further to application on site. What was the motivation? And when I started the motivation, all seeing that iconic design in London, in St. Pancras, how earlier when that was built, the material was expensive and the labor was expensive. So that's mean when we design, we have to optimize as much as we can do. Also, we have a fantasy nice shape that please the client and the architect. So the question is how and when we could come back to this. So that was the motivation. Will 3D print be the way forward to have more optimized design? So this is the vision. And I think this is the vision for all the AM industry users in all different fields, is to have an optimized structural engineering designs using this novel manufacturing technique. But everything takes steps, and we're still earlier, we were in early stages, but we still have that limitations. But the more we highlighted it, we know the direction. These were limitations, but we're still improving it, but it's still coming. So we have that limitations on the design softwares, the techniques, the materials, and the knowledge. And also, it's really important for the market to know what application or when we can use it, because you want to get some feedback from it. So when you start, you would see that limitations. If you have your printers in-house and you start printing, these are my early stages printing, and you can see the porosity, you can see how the melting is not proper, you can see how different type of failure you can recognize, and everyone will have it, you would see that. So there's a learning process for us. I will just go quickly with you to see how the printing process, what we printed in my project, what are the tips and to take it forward. So we know that we have AM categorized the AM to 7 process. So the one highlighted in gray is being used in the concrete, but the one has been highlighted in cyan is which is the powder bed, and the DAD is being used in the metal. So when anyone will start, you will ask yourself, is it powder bed or is it DAD? And for construction, in my design, in my research, I've used the DAD, not the powder bed, because I believed it has high deposition. I'm not limited with the room chamber. I could have more high material utilization, and the time needing was different. And mostly that governed me is the size, because we're talking about construction. In my research, been very lucky to collaborate with Estilo in London, with Autodesk in Birmingham, RamLab in Rotterdam, and we used the Autodesk movable cabin there. So we've used the WAM technology, and we've done different testing. For you guys who doesn't know what's the WAM technology, this is a quick show us how the printing process happens. The robots, we can see it's like a welding process, and we can see how that bead has been printed. I shouldn't have taken the pictures, but I took safety when I've done that. So it's like a welding process that's building us a layer on layer, or doing filling a 2D while we're doing that. If we went deeper to see how this weld being, or that bead being built, we can see, yes, it's like a wire that's going down, melting and filling things, but how the interaction. I'm asking questions that have been asked while I'm doing the research, because we want to make sure that it's giving us a good, strong material. And these are the 3 main steps that all 3D printer users need to follow, or already following, which are, we need to optimize the parameters. And for us who's new to this, we need to see how to optimize what's the speed. Coming from civil engineer background, and need to learn about welding, what height, what speed, what's the voltage. Because if you see in that white picture, you can see different beads, and all have different widths, different height, and different porosity if we're not doing the right optimization. So we need to do this exercise before we start, unless we have softwares now that we could depend on it, but we need to do that exercise to optimize our bead. And then we need to do another exercise to optimize that between each layer bead, which is called step up or step over distance, because all this will affect the overall results. Then in structures, this is something that we need to keep in mind, that our thickness, and when we are doing the design range between 10 millimeter till 20, so you won't have bead width that width when we're doing the WAM technology. So we need to think about the path planning process. Are we which one to use? And bridging between both technology, I would say, if you are familiar with these rasters, exact contour, and so on type of path planning, I would go for the rasters or the contour, and mostly the rasters, because it has that welding basis, which has already a benchmark design code in the structural industry. So the rasters was followed in the application that we already done in my PhD work. So what we printed is, you can see here with the one on the top, the welding torch, we can see a plate, and we can see the lines, and we can see the rectangular shape, and we can see the eye section. So the first shapes were fine with just one bead, but with the eye section, yes, I started with an eye section. I know the technology is for more optimized components, but we need to benchmark it. And coming from that old school, I thought the R section is a starting point, because all our design code talking about the R section, the normal in design, in addition to circular and hollow sections. But for the R section, and talking about these depth, the 10 and 20 millimeter, so one bead we can see it's not enough, so we need to think about the path to fill this 2D. And I'm highlighting this because I want to share that knowledge to push it forward. So which is the path, and which was the more optimized one that was happened in the research, and we studied we printed different shapes, and we studied the material for that to see what's the difference and how to do it. So path planning is the next step, and then printing strategy is another step. From structural point of view and construction, we need to see where is the failure will happen. So we need to ask the client, what's the purpose of that joint, or what's the purpose of that component, so we could know where's the failure. So in my research, in collaboration with RamLab and TU Delft, I've asked them to print that beam to column connection. And because I've said a beam to column connection, so we thought about where the failure will happen. So it's going to happen in the joint. So in the joint between that column, I don't know if you see it, that column and the beam. So then this is the key points where it's highlighted in yellow. This is the transition zone. So when we've done the printing, we thought about a special process to make sure this is our strength. And the printing strategy was a two-directional because of the shape. So we started printing the columns and then the beam. So these are different steps. The more we know about it, we take it ahead in the concept starting point. So summing up, after all this learning process, from seeing that porosity in the beads and in the walls to the learning process in the project, these are the printing components that's been done. And these could see a potential application. How I'm saying that, why? So I would start with the Autodesk plate, which we printed it in Birmingham. It was a starting point, a plate. This is how you would see it. But how I will see it is for an old factory, which has a rusted, and after time it has a weakness in the plates and the flanges of the printing. The robot can go there to that factory and print extra layers to thicken the design to make sure it is safe. So this could be one of the application is the enhancement stage. Yes, we still need to research what's durability, but it could be, or how the connection between the old and the new steel would happen, but enhancement is one of the way. The other application was at Stilo, where we are thinking, when we think about fabrication, we want to minimize the number of labors. So we need to automate the welding process. So we could think about that one technology could be used as printing the fin plates on site, so, or in the factory instead of chopping and cutting things. In that R section, the rectangular hollow section and the beam, it was a replication for the current design. We see it already in our houses and everywhere, but we need to start somewhere to benchmark it. So all this has been a learning process for us to push that forward. But again, coming from, that was the printing, and this is our beam. This is me in the lab, and just showing you the size of the printing. It took us 100 working hours, but it was mostly learning hours there. So coming from back to the civil world, yes, we did the printing, we learned about it. We want to see how to make sure what's going inside and how to convince a future user that it is safe, and we could take it forward. So we did XCT scan and we did a destructive test. When we started with the XCT scan, we did in collaboration with Work Manufacturing Group, we studied this. We scanned most of the element to see what's the relation between the printing process, tensile testing, characterization, and inside the component. And you would be surprised to see all this. It was mostly my printing, so I would expect to see a lot of porosity in all this. It was so. We know why we have porosity, we know the location of the porosity, and we know the links now between the porosity and the tensile tests, the readings that we need when we design the characterization. We've seen how the printing we can see how the interfacial, so if you can see between each layer these fancy colors in the left, we can see why we are having it. It was because I haven't optimized the printing of the step over between each layer. It wasn't right, and we can see the density is different. That's why we have it in between, and we can see how the porosity are in between these layers. So it was learning process, and the funny part is after exploring this, we know the parameters, we know the XCT, we've studied I'll come back to this, we've studied then the tensile test, which I'll explain later. For the beam to column joint, when we did the XCT scan, and because I've showed you how we did that transition between the beam and the column, and you can see in the right picture that the white color, the white here, the white printing or the white captures photo because it was dense printing. And this we can see it with the XCT scan, and we can also see it later with our results. So this is due to this, which I said, like the tapered printing layers before going ahead. And we can see it. So we studied the XCT, and then we had to do the tensile or the destructive test to see how strength, what's the strength, what's the F yield, what's the F ultimate, because this is any starting for designing process. We did tensile, we did impact, and we got really brilliant results. For the mild steel, we could see how we achieved the design code, the current Euro design code limitation with the porosity, but with a minimum acceptable porosity, which was less than 1%. So I'm highlighting this here, and for the high strength, we achieved the 10% elongation, we achieved the F ultimate to F yield percentage, and we've seen the coupling cone failure. So why I'm highlighting this, because it's an early stage for AM in metal, in construction, and we already know that limitation and the porosity. So when casting started, we accepted a minimum percentage. So in my research, I'm trying to push that forward and accept minimum limitation at early stages, because building confidence is vital for structure, because it is our safety. We're living in the houses or we're stepping on the pedestrian. So after seeing that we are applying that, we're getting that, we've done a beam to column connections test. We've studied the stiffness and the rotation, yes, for a conventional beam, because later on you would see a flowery, you could see a star beam, you could see whatever design beam, but we need to start somewhere with something to bench it. So that was the starting point, and it gave us a results that is applied with the design code and where it could fit. So that was very optimistic to take that and to share that knowledge and to take it forward for future application. That we already seen the technology in the gas and oil. So why not in construction? Why not doing that in our fabrication workshop? Yes, we've seen MX3D printing that fancy joint and that columns. So the more we did that research, we could take it forward. But my advice is to always ask, where's the load path? Ask that structural engineer. Ask them what's the key elements, where the failure will happen, so we think about it. And also, the more we know about it, so once we know about these key, where the failure will happen, we will think about it, because we want to push the industry further. Don't take it as just a fancy shape, ask them. And also, as a starting point, we could design things that is not a key element in the building, but it could be a plan where other element could replace it if anything happened, because we still doesn't know the future of it. So it's a mix of words, it's a mix of positivity and challenges, I would say that way. So if we think about the challenges, like any new innovative technology, we still doesn't know what's the long term. We still have imperfections. We doesn't have enough standards. We still see the porosity. But looking at the positive side, yes, this could be the way further to engineer our design to have a sustainable design. We always hear about the carbon, and we want to minimize the carbon effect for our environment and for the sustainability. So this could be a way forward for us to optimize our design, to have more parametric design. We've seen it. We could apply it now with the AM technology. And if you ask me about porosity, I would tell you, start using it. You've seen the static word load here. You could start using it in the building. Avoid bridges for now, because you don't want to be questions about fatigue and about future crack, but you could find a way by telling them, yes, in the building, I don't need to specify this for now. So it's innovative, but we can take it forward. Again, I'll ask this question when it's us, it's the younger generation, and also the big generation who's leading now, and take that, all the CEOs and all the directors who could make a step to take it forward. Believe in the technology, give it a chance, and let's come back to this more optimized design. And yes, let's talk about it and let's raise awareness about it. And thank you all for listening. And if you have any questions, I'm all with you. Thank you.
Thank you for your presentation, Zaina. It was very interesting. I hope the participants enjoyed it as much as I enjoyed it. We have a few questions for you.
Yeah, sure.
First of them is, what development do you need in metal AM processes to push AM construction to the next level?
What's that?
Okay, I will repeat again.
Yes,
What
please.
developments do you need in
Yes.
metal AM processes to push AM construction to the next level?
So I would say softwares, because we want to have a more useful softwares for structural engineers, because we're designing, okay, we use a lot of hand calculation to do our designs, but we depend also on softwares. So we don't know how much we could really relate the current results from the AM or the materials with the already designed software we are using. So that was the main purpose of this research, is to benchmark it with the current design code to see how much, because we see how much we can use the current design code. But coming back, how we want to push it forward is, I believe, like, been working in this for the last 4 years, I believe the more we share where are we in the AM, share what what's the new addition. We don't want just to hear that we printed this or this is what we printed. No, share how we printed it. I know at the end you need to prototype it. I know it's also want to be a business for you or for the company, but also when you give that knowledge to the engineers that this is how it's been done, this is the results, I think they will believe in it more. And then they will take it forward, because so yeah, I hope that I've answered that question. So it's about, yeah, because I'm bridging between both, so it's just share with the engineer, because we need to believe in it. We need to have that confidence in the outcomes from it before using it in our buildings.
Amazing. Yeah, we have time for one more other question. We have a question here, say, have you started qualifying components for use? How would you approach that in your industry?
Yeah, so I would say we could start prototyping things. So we could prototype a connection, and we could use the same method that I've done it for prototyping, like a big fancy connection in special fabricator or something. You could start printing it, then you could get that qualification by getting the XCT scan, you get the results, and then you certify it. I know this is an old way, and it's already happening with the oil and gas now, but if it's happening in the oil and gas, and construction always is slow in adapting a new technology, and this is something that's been for ages. So we could follow the same steps in giving that certification for either prototype connection or damper in earthquake or any new applications that it's well used at some point. So we could think that's what's needed to build that confidence, if I got the question right. You're muted, Malika. Awesome.
Zaina, for the insightful presentation, and as well working through your PhD research. We hope to see you a doctor soon. All the best with that. Thank you for making time for this session. You can put your mic and camera on.